In geometric sequences, we actually can also sometimes find the sum of an infinite series. This wouldn't really be possible in arithmetic sequences because the numbers would just keep getting bigger and bigger, so there wouldn't really be a final sum that you could come to if there were an infinite number of terms. In a geometric sequence, sometimes you've noticed that the terms actually converge down to a certain number or to zero or something. So you can actually add and find the sums. So we're going to take a look at that now. So the sum of an infinite geometric sequence, if you have an infinite geometric sequence, that is what's called a series. So an infinite geometric series is the sum of a sequence. So the summation notation for that would look like this. Sum of k equals 1 to infinity, right? There is no final n number of a sub 1 times r to the k minus 1 power. So in other words, it's geometric. We're going to be summing it from 1 to infinity. Okay, now if the series converges, that means that it approaches a certain number. Okay, that means that r, the r value, is less than 1. So I put absolute value around it because it could be positive or negative, but if it's less than 1, then it will converge, okay? And then you can find the sum, and the sum is, I like to put the little infinity there, it's an infinite sum, is just the first term divided by 1 minus r. Okay, and it can only be used when the series converges. If it diverges, that means that the absolute value of r is greater than 1. R can't be 1 or you're not going to get a geometric sequence, right? So that means that the sum approaches infinity, negative infinity, or it oscillates. So like, for example, if r was -2, then the sum would not really approach positive infinity or negative infinity, but would rather be going way big positive than way big negative and such. Okay, so let's highlight this formula and see when to use it, because I've given you a lot of little definitions and stuff now, and you might be a little confused about converge and diverge. I think with a concrete example, you'll see that it's actually pretty straightforward. So for our example, let's look at this the series of 81 plus 27 plus 9 plus 3 plus a third plus dot dot dot, right, to infinity. So as you can see, this sequence of numbers is 81, 27, 9. They are getting smaller, right? So in other words, our common ratio, it looks like they're dividing each term by 3. So the common ratio is 1/3. So when the ratio is less than 1, then the series is going to converge to a number, right? Because if you think about these numbers, as they go on, they'll get closer and closer to 0. So you'll be adding less and less and less on. So that means that the sum of them is mostly here. It's mostly all here. Then the next number is 1/9. That's pretty small. Then 1/27. I mean, so, we're going to be approaching a certain number. And that number we can find is the sum is the first term. Well, we know that a sub 1 is 81. So 81 divided by 1 minus r. So 1 minus 1/3. Okay, so 81 divided by 2/3 is equal to 121.5. Okay? So, like I said, notice if you add 81 and 27, right, you get 108 plus another 9, that's 117, 120, 120 and a third, and you keep adding. See how you're getting really close to, and then this is the number you'll be approaching, 121.5. Okay, let's look at another example. So if you have the sum from k equals 1 to infinity of 2 times 4/3 to the k power, okay, we'll do the k minus 1 power. Notice that it is a geometric infinite series, okay, because it does fit the pattern. However, because the r value is 4/3, that's greater than 1, so this number is just going to be getting bigger and bigger the more numbers that we add on. So we cannot say what number it approaches. So it is called that it diverges. Okay. Our first example converges to 121.5, okay? Converges on a certain number. Diverges means it's just going to be infinity, negative infinity, I guess in this case, infinity, okay?